Hello everyone. This talk presents Affordance-First decomposition for continual learning in video language understanding. The central challenge is simple. A video language model must keep learning as new domains and question styles arrive, but it should not forget how to reason over earlier videos. Our answer is AFD, a framework that separates a stable interaction-centered representation from a small, adaptive reasoning scheduler. Why is this difficult? In real systems, video streams are non-stationary. A model may first answer questions about daily activities, then temporal localization queries, and later open-ended explanations. Naively fine-tuning the whole model makes the representation drift, while storing and replaying old videos is expensive and can violate privacy. So the question is not only how to adapt, but also where stability should live. Existing continual methods often use prompts, adapters, or post hoc regularization. These are useful, but they leave two issues. First, they do not explicitly define which part of the model should remain task invariant. Second, plasticity is usually budgeted with fixed capacity or static routing. As a result, the model may spend capacity everywhere, even when only a small portion of the reasoning path conflicts with past tasks. The main insight of FD is to decompose the problem before learning. Videos are first converted into affordance tokens, such as open, pick, hold, pour, or move. These affordances describe object action regularities and change slowly across domains. The language query is then handled by a lightweight LLM scheduler. In other words, the affordance head is the stable substrate, while query-routed adapters provide plasticity. Here is the first component. A spatiotemporal encoder extracts video features. The shared affordance head predicts a distribution over an affordance vocabulary, keeps only the top L categories, and builds continuous affordance tokens. These tokens are projected into the LLM hidden space as keys and values. Stability losses, including weak action span alignment and teacher consistency, are applied only to this head, so the video evidence remains reusable across tasks. The second component is the LLM scheduler. The question is tokenized by the same LLM and pooled to drive up a layer router. At selected layers, the router mixes several low-array experts. A FD also measures gradient conflict. When the current update is anti-aligned with past directions, it throws the low-array rank, but only for the responsible expert and layer. This makes capacity expansion targeted rather than uniform. Training follows the same separation. Task supervision trains the routed scheduler to produce answers, spans, or step sequences. The affordance loss stabilizes the shared video substrate. Question-only replay distillation stores diverse past questions, not past videos, and uses current clips with the previous model as a teacher. This gives a memory-friendly and privacy-friendly rehearsal signal, while avoiding broad drift of the visual substrate. The empirical results support the design. On domain incremental video queue over 6 datasets, a FD reaches 51.6% average accuracy with only 1.8 points of forgetting, outperforming DIM and Bicycle. On VLCO bench, it obtains the best results across moment query, natural language query, and visual query protocols. On time incremental IVQA, a FD again achieves the highest average accuracy, 39.5%, and the lowest forgetting. The ablations show where the gains come from. Removing affordance tokens causes the largest drop, almost 3 points in average accuracy, and substantially higher forgetting. Removing the router, rank growth, or question-only replay also hurts. Diagnostics further show that affordance tokens are stable. Cross-task CK is about 0.91 for affordance tokens, compared with about 0.70 for backbone features. Rank growth is sparse and concentrated in mid-level layers. To conclude, a FD makes the stability plasticity split explicit for continual video language learning. It anchors evidence in a slowly varying affordance substrate, then adapts with query-routed, conflict-aware low-array experts. This simple division gives strong accuracy, low forgetting, and interpretable diagnostics, without storing old videos. The broader message is that continual video language models should not only learn new tasks, They should also know which structures are meant to stay stable.